So let's take a look at this simulation. Suppose I have a distribution which is not normal. My goal is to construct a distribution which is normal, but I cannot change the population. This is my population, this is the behavior of my population. I'm taking samples from this population. And then I find the mean of those samples. I take another sample, I find the mean of that sample. I take another sample, I find the mean of that sample. I repeat this process thousands of times. I can increase the sample sizes to get a better mean, and then the distributions becomes much more normal. Just take a look at this. This is the basis for central limit theorem. Just let me write down what's happening here. What is the steps? What's the process? And why we need that. Just an introduction to central limit theorem for you. In the central limit theorem, the central limit theorem, as we saw in quiz 3, we have populations that are not normal. We take random samples from that population. We find the means of those samples, so X bars. Then we graph X bars. So now your variable is the mean of the sample. This is our new variable. The distribution of X bars are normal. So it gives you normal distribution. On the horizontal line, you're going to use X bar as the new variable. And we call it the sampling distribution. The sampling distribution of sample means X bars. And the central limit theorem says mu sub X bar, the mean of this distribution is the same as the mean of population, and the standard deviation of this distribution, sigma sub X bar, is standard deviation of the population divided by square root of n. As you remember, when you did quiz 3, the mean of that new distribution was almost the same as the mean of the population, the census. But the standard deviation that you found was 3.5, which was much more smaller than the standard deviation of your population. It's because of central limit theorem. We're going to discuss this later.